In this tutorial, we will be discussing an introduction to reaction rates. In kinetics, we study the rate at which a chemical process occurs. Besides information about the speed at which reactions occur, kinetics also sheds light on the reaction mechanism, which is exactly how the reaction occurs. There are several factors that affect the reaction rates. Physical state of the reactants is one of them. In order to react, molecules must come in contact with one another. The more homogeneous the mixture of reactants, the faster the molecules can react. Another factor is the concentration of the reactants. As the concentration of reactants increases, so does the likelihood that reactant molecules will collide. Temperature is another factor. At higher temperatures, reactant molecules have more kinetic energy, move faster, and collide more often with a greater energy. And finally, a catalyst. Catalysts speed up reactions by changing the mechanism of the reaction. Catalysts are not consumed during the course of the reaction. They just move things along faster. So what exactly is a reaction rate? Rates of reactions can be determined by monitoring the changing concentration of either reactants or their products as a function of time. Reaction rates are how these concentrations are changing per the time is allowed. In this reaction, the concentration of butyl chloride, C4H9Cl, was measured at various times. So for instance, time 0 when it started was 0.1 molar. Then after 100 seconds, it dropped down to 0.082. Notice that it's decreasing. That's because this is on the left side. That's the reactant. It's being used up in the reaction. The average rate of the reaction over each interval is the change in concentration divided by the change in time. So, for instance, from 0 to 50, for the first 50 seconds, it changed from 0.1 molar to 0.0905 molar. So the change of this concentration divided by the change in time gives us the rate of the reaction. Notice that the average rate is given to you in molarity per second. Note that the average rate decreases as the reaction proceeds. So we start at 1.9 times 10 to the negative 4, and then by the time we get to 400 seconds or so, we're down to 1.01 times 10 to the negative 4. This change right here, they're both times 10 to the negative 4. This is because as the reaction goes forward, there are fewer collisions between the reactant molecules. The concentration of this chemical is decreasing, and so the collisions then are decreasing. A plot of C4H9Cl versus time for this reaction yields a curve like this. So this is the reaction we saw on the previous slide. The molarity, the concentration is going down as the time is going up. And here, at the very beginning, it goes down fairly fast and then it levels off. That's because the concentration is decreasing and the collisions are decreasing. The slope of a line tangent to the curve at any point is the instantaneous rate of that time. So we could take a tangent line to find the instantaneous rate. All reactions slow down over time. Therefore, the best indicator of the rate of the reaction is the instantaneous rate near the beginning of the reaction. In this reaction, the ratio of C4H9Cl to C4H9OH is 1:1, the coefficients. Thus, the rate of disappearance of C4H9Cl is the same as the rate of appearance of C4H9OH. So as this one goes away, this one is appearing. Notice this negative sign here. That's because that's the reactant. That's disappearing. And this one over here is positive because it is appearing. What if the ratio is not 1:1? For instance, we have 2HI that's breaking down into H2 and I2. In such a case, notice we have a 1/2 here. That 2 is coming from the HI. So in other words, this is going to disappear faster than these reappear. Once again, that negative sign here. To generalize then for the reaction, for reactant A, we have 1 over little a. Notice the minus sign. Reaction B, 1 over little b. Reaction C is a product, so it's going to be positive, 1 over C. And reaction D, 1 over D. They're all equal to one another, with the exception of this being negative, because as these are going away, these are appearing. So let's do a practice problem with this. Consider the balanced chemical equation. In the first 10 seconds of the reaction, the I minus drops from 1 molar to 0.868 molar. Calculate the average rate of reaction in this time interval. Well, first of all, let's use this equation here to determine what's going on as far as the rate's concerned. So the rate is equal to negative 1/3, because there's a 3 here, the change of the concentration of I minus over the change in time. So that means the rate is going to equal to negative 1/3. The change is 0.868 minus 1.000 molar. The change of time is the first 10 seconds, so it's going to be 10.0 seconds. Calculate this out. The average rate of this time is 4.40 times 10 to the negative 3 molar per second. Let's take the same equation and do one more. Predict the rate of change of the concentration of H plus, so we're looking at this one now. That is the change of H plus over the change in time during this time interval. So once again, the rate is equal to the negative, because it's a reactant, 1/2, because of the 2 here, change of H plus over the change of time. We can rearrange this equation to say that the delta H plus over delta T is equal to, because that's what we're looking for, we can multiply this across and take that negative sign with it. Negative 2 times the rate. We know from our previous question the rate at this time is 4.4 times 10 to the negative 3. We also know from this over here that all of these are equal to each other. So that's why I'm able to use the rate from the previous question. So that means the change of H over the change in time is equal to negative 2 times that rate. That comes out to be negative 8.80 times 10 to the negative 3 molar per second. And that's how you solve for the average reaction rates.